The problem is optimal binary search tree. In this video, I am going to talk about what is binary search tree. Then, what does it mean by optimal binary search tree? The problem. Then, the dynamic programming approach for solving this problem. So, I'll take an example and I will solve it. And I will also use the formula and show you how the formula is generated. My focus will be on showing you how dynamic programming is working on this problem, right? Instead of just showing you a shortcut how to fill up the table and get the answer. Let us start with binary search tree. See, if the set of keys are given here and the purpose is to search the keys. If already I have the list of elements and I want to search some element. So there are different search methods like linear search and binary search. And also we have a data structure called binary tree. Can we utilize binary tree for searching purpose? Let us see. I will arrange these elements in the form of a binary tree. So I will create a binary tree out of these elements. So I'll keep root as 40 and 20 as its left child and 10 as its left child and 30 here, 60, 50 and 70. Now you can see that the elements are arranged such that for any node, all the elements on its left hand side are smaller, all the elements on its right hand side are larger. For 40, all these elements are larger, and for this 60, this element is larger and this element is smaller. Likewise here also. So the benefit of arrange this type of binary tree is that it is useful for searching. Suppose I want to search for a key element 50, then I can start from here. Is it 50? No, 50 is greater than this one. So definitely it's on the right hand side. Go here and check it. Is it 50? No, the key value what I am searching is smaller than this one. So go on the left hand side. Yes, key is found. So that's how. What is the time taken for searching a key element? The maximum time will be if the element is in the leaf. So what is the amount of time? So this is height of a tree, and the height of a binary tree is minimum log n, and this is minimum height only. So the time taken for searching in a binary search tree is log n. Now one more thing we have to consider here. When I am searching for the key like 50, I got the key. Suppose I am searching for a key element that is 45. Is it there? No. If I search for it, 45 is greater and 45 is smaller than 60. 45 is less than 50. So my search will terminate here and the search is unsuccessful. So search may be successful or search may not be successful. That is, it may be unsuccessful when you are searching for the keys. Now next, I will show you for a given set of element how many different binary search trees are possible. I have taken just 3 keys. Let us see how many different binary search trees are possible. So for these 3 keys, 10 as a root and 20 as its right child and 30 here. So 10, 30 and 20 on this side, 20, 10 and 30 on this side. So for 3 keys, there are 5 different binary search trees possible, right? So for n keys, how many different binary search trees are possible? 2n cn by n plus 1 binary search trees are possible. So for 3, this will be 2 into 3 c3 by 3 plus 1, this will be 5. So 5 different binary searches are possible for 3 keys. For n number of keys, these many are possible. We will see what is the cost of searching in each tree. See, the cost is dependent on the number of comparison required for searching for a key element. So in this tree, if I am searching for this key element, then the cost is 1. If I search for this one, then I have to make 2 comparisons. And if I have to search for this one, I have to make 3 comparisons. So what is the average number of comparison? Average number of comparisons are, there are total 3 nodes. So this is 6 by 3, that is 2. Likewise, if I consider all of them, then this is 1 and this is 2 and this is 3. So this is 1 plus 2 plus 3, that is 6 by 3, that is 2. And here it is 1 and this is 2 and this is 2. So this is 5 by 3. So this is less than 2, right? And this is 1 and this is 2 comparison and 3 comparison. So this is 6 by 3. 1 comparison, 2 comparisons and 3 comparisons. So this is also 6 by 3. So you can see that out of these 5 trees, one of the tree I got less number of comparisons. That's average of comparison is less. So that's what this is, a balanced binary search tree. So why we got less is the height of this tree is less. So that's why this is balanced binary search tree. So I have shown you what does it mean by height balanced binary search tree. Now let us come to the actual problem, that is optimal binary search tree. So in this problem we consider that if these are the keys available, then we also consider what is the frequency of searching of those keys. If the keys are having some frequencies of search, let us say the frequency of searching 10 is 3 and this is 2 and this is 5. So this means that all the keys will not search them with the same frequency. Some keys are there that are more frequently used, so we search them more frequently, more oftenly, and some are rarely used. So like that, who is having highest frequency? 30 is having highest frequency. Then if the frequencies are defined for each key, then what will be the cost? So I want to know which tree organization will be optimal or better. So let us check them. See, the number of comparisons required for this one is 1, but its cost is 3, frequency is 3, and this frequency is 2, and this frequency is 5. So how much this will be? 15 plus 4 plus 3, 18. And this is 3, and this is 2, this is 5, and this is 2. So this is 10 plus 6 plus 3. So this is 19. And here the frequencies are, this is 2, and this is, the number of comparisons are 2 and its frequency is 3. So this will be 3 into 2. And the number of comparisons required, that is the level, is 2 and its frequency is 5. So this is 10 plus 6 plus 2. This is 18. And here it is 5, then 10, that is 3, and this is 2. So this is 5 plus 6 plus 6. So this is 17. And this is 5 into, this is 2, and this is 3. This is 9 plus 4 plus 5, 18. Now the cost of the trees are different. You can see that this tree organization has given us best result. So that is optimal binary search tree for these 3 keys. Though it is not height balance, this was height balance. Now the height is more, but based on the frequencies, that cost of that binary search tree is minimum. So that's what the problem is. If the keys are given and the frequencies are given, we have to find out which tree organization will be optimal based on the frequencies. Now I will take a problem and I will solve it using dynamic programming approach. Here I have keys 10, 20, 30, 40 and their frequencies are given here. For finding out optimal binary search tree for these set of keys, I have created a table here. I will be filling the values in this table and then that will help me to generate a table. Here the keys are 1 to 4. Now the table, you can see that it is starting from 0 onwards, right? But the keys are starting from 1 onwards. I have taken from 1 onwards. This is from 0 onwards, so that it is suitable for formula. Let us see how to solve this problem. Let us call these rows as I and columns as J. Now first of all, we will find out those values which are J minus I is equals to 0. So for which values it will be? J minus I will be 0. This is 0 minus 0 is 0. 1 minus 1 is also 0. 2 minus 2. 3 minus 3. 4 minus 4. All these are 0. So it means I'll find out the cost of 0 comma 0 and 1 comma 1 and all these. So it means I'll fill up the diagonal. And for the diagonal, I'll first fill up with all zeros. This is the first step. Now I will find out this diagonal. So in this one, J minus I value should be 1. J minus I equal to 1, then what it should be? So this is 1 minus 0 is 1, 2 minus 1 is 1, 3 minus 2 is also 1, 4 minus 3 is also 1. So this is 0, 1, 1, 2, and 2, 3, 3, 4. So I'll find out the cost of all those. Cost of 0, 1, cost of 1, 2, cost of 2, 3, and cost of 3, 4. Now we will start filling the values. Now see, 0, 1 means I'll be considering just one key, that is key 1, 10. What is frequency? 4. So the cost is 4. And C of 1 to 2, just ignore this first value and take this one. So this is the key. Second key is 2 and the cost is 2. So yes, this is 2. And this is third key. Third key is 30 and its cost is C, that is frequency is C. So the cost is 6. And this is 40 and its frequency is 3. So the cost is 3. So 4, 2, 6, 3. So I got the answers as 4, 2, 6, 3. So I have considered just one node where j minus I equal to 1. Now next we will go for j minus I equal to 2. Now when this j minus I will be equal to 2, so this will be for 2 minus 0, this is 0, 2, and 3 minus 1, this is 1, 3, and j will be 4 and I will be 2, so this is 2, 4. So for these things, j minus I value will be 2. So it means I'll be considering two keys. So I will consider first key and second key first. So that means I will take this one first. So cost of 0, 2 I will find out. This is 0, 2, right? I am considering two keys. So what are those two keys? Just ignore 0. Start from 1. So key 10 and key 20. What are their frequencies? 4 and 2. Let us see, using these two keys only, what is the minimum cost binary search tree or the optimal binary search tree I can generate just by using two keys. So for two keys, what are the possible binary search trees? 10 and this is 20. That is, first is the root and this is, second one is the root. So 10 will be on this side. So what is the cost of this? So directly I will calculate. See, the frequency is 4 and this is 1 time. And this is frequency is 2 and the number of comparisons are 2. So how much this is? 4 plus 4, it is 8. And this is 2 into 1 and this is 4 into 2. So one comparison required for this and two comparisons required for this. So this is how much? 8 plus 2. So this is giving 10 and this is giving 8. So which one is minimum? This one is minimum. Minimum cost is 8 and which key is forming a root? 1. So I will fill up this value 8 and the root is 1. Now I will show you how I can apply the formula here. Now before showing the formula, I will use one value, that is weight of 0 to 4 for example. Then this means sum of all the frequencies from 1 to 4. Actually we have frequencies from 1 to 4, but we'll write from 0 to 4, right? We are starting from 0 so that we can make a formula. So C of 0 to 4 means sum of all the frequencies from 1 to 4. So let us see the formula. See, this is, the cost is 8 I got. Now here I was taking root as 1. So this is C of 0, 0 on the left hand side. Then C of 1, 2 on the right hand side. Plus weight of 0 to 2, right? So this is 0 to 2. Let us check from the table what we got. Will we get this value as 8 or not? Let us check. C of 0, 0, how much? 0. Plus C of 1, 2. C of 1, 2 is how much? 2. 2. Plus weight of 0 to 2 means I should add all the frequencies from 1 to 2, 1 and 2. So already I have this 4 plus 2. So 4 plus 2. So answer is 8. Now how the same formula is applicable on this side? See, this one is, I am taking 2 as a root. So 1 on this side. So C of 0, 1 plus C of 2 to 2 plus weight of 0 to 2. So from the table, let us see 0, 1. 0, 1 is how much? 4. Plus C of 2 comma 2 is 0. Weight of all these, that is 4 plus 2, is 6. So how much this is? 10. Yes, we got the same answer. So either I just check them with the height, I am getting the same answer, or else I am using the formula. So I am not showing the complete formula, just I am applying it here. So which has given us the minimum result? 8. So that I have written there. Right? Now I have to find out 1 comma 3. C of 1 comma 3. Just ignore 1. So start from 2. So 2 to 3. So I will be taking keys 2 and 3. Already 1 and 2 all finished. So 2 and 3, because every time we will be taking just 2 keys. So keys are 20 and 30 and their frequencies are 2 and 6. Now what are the different trees possible from this one? I can make this second one as a key root. So this side will be 30. Or I can make third one as a root. So this side will be 20. Now what are the costs for this one? This is 2 into 1 and the number of comparison for this one will be 2. So this is 6 into 2. So how much this is? So 2 plus 12 is 14 and this is 1 into 6 and this is 2 into 2. So this is 4 plus 6, that is 10. Who became root here? Third key. This is the second key and this is the third key. So third key became a root here. So this is 10 and third key became root. I will not use the formula, already I have shown you. Now let me finish another value also. Now next key is this one. This is 2 comma 4. So 2 comma 4, C of 2 comma 4. So ignore 2, we'll be taking third key and fourth key. So third key is how much? 30 and its frequency is 6. Fourth key is 40 and its frequency is 3. Now what are the trees possible? So if I make 30 as a root, then 40 will be on the right hand side, or else 40 as a root, then 30 will be on the left hand side. So two different trees are possible out of this, right? Let me put the cost directly. So the frequency of this one is 6 and the number of comparisons required are 1, and this is a 3 and the number of comparisons are 2. So this is 6 plus 2, 6, and that is 12. This is 3 into 1 and this is 6 into 2. Its cost is 6. So this is 12 plus 3, that is 15. So who has given us the minimum result? 12 has given us the minimum result. And what is the key here? Third one is the key here. So answer is 12 and 3 is the key. So 3 will become a root, third key will become a root. So that's it. We have filled up this diagonal where every time we were considering 2 keys. Now we have to fill up this diagonal and we have to consider 3 keys at a time. Now j minus I equal to 3. So what are the possibilities? J is 3 and I is 0. So this is 0 comma 3. And J is 4 and I is 1. So this is 1 comma 4. So these are the two possibilities. So I should consider first 3 keys and then what, that is 1 to 3 and then 2 to 4. So 3 I should select. So let us see if I select this first one, that is 0 to 3. So just ignore 0 and take the keys. So the keys are 10, 20 and 30. First key, second key and third key. And the frequencies are 4 to 6. Now what are the trees possible with these 3? If I take 10 as a root, then on this side I can get 20 and 30. This is one possibility. Or 10 as a root, then 30 and 20. This is another possibility. Just 10 as a root. So 10 is 1 as a root, right? 1 as a root. Then if I take 2 as a root, then what are the possibilities? 20 is here and on the left hand side is 10 and the right hand side is 30. If I make 30 as a key, that is root here, 3 as a root, third value, then 30 on this side, then left side it can be 20, 10 or 30 as a root, 10 and right side 20. So with the 3 keys, by selecting any one of the key as a root, there are total 5 different trees possible. Now out of this, which one is minimum? Which one is minimum? So for this, I will use the formula directly, right? I will not calculate them. So formula, if you remember this one, sum of the frequencies. So we have to take from 0 to 3. So if I find out weight of 0 to 3, directly I will find out how much it is. 4 plus 2 plus 6. So this is 12. So let us use this 12 every time. Alright. So what is the cost of this side and this side and this side? See, here who is root? 1 is root. So if 1 is root, then this will be C of 0 comma 0 plus C of 1 comma 3 and plus weight. Weight is how much? 12. I'll directly write on this one. Then for this, when 2 is there as a root, so this is 0 comma 1 plus C of 2 comma 3 plus 12. And on this side, C of 0 comma 2 plus C of 3 comma 3 plus 12. Out of this, I have to select any one of them that is giving me minimum. So that will be the cost of C of 0 comma 3. C of 0 comma 3. So 0 comma 0, that is 0, plus 1 comma 3, how much? 10 plus 12, 22. 0 comma 1, how much? 4 plus 2 comma 3, how much? 2 comma 3 is 6 plus 12. So this is 22. Then 0 comma 2, how much? 8 plus 3 comma 3, 0 plus 12. This is 20. So 22 and this is also 22. Which one has given minimum result? This is 20. So 0 comma 3 is 20. And which root has given us answer? 3. Third root has given us the answer. So this is third root has given us the answer. So third key should be a root. I have to find out next value, this one, for 3 keys, and that is 1 comma 4. C of 1 comma 4. So what are the keys? Just ignore 1 and start taking the key from 2 onwards. Second key, so that is 20, and the third key, that is 30, fourth key 40, and the frequencies are 2, 6 and 3. Right? So I will not draw all possible trees now. Directly I will use the formula and solve it. So for that I will find out the weight. So W of 1 comma 4. So in this skip 1 and remaining we have to find out. So it's nothing but sum of all these frequencies. So 2 plus 6 plus 3. So this is 11. Now let me use the formula. C of 1 comma 4 is minimum of C of, second is the root, so 1 comma 1 plus C of 2 comma 4. Or C of, third key is a root, so 1 comma 2 plus C of 3 comma 4. Fourth key is a root, C of 1 comma 3 plus C of 4 comma 4. And at last I have to add that weight, that is 11. So let me write down these values. 1 comma 1 is 0 plus how much this is? 2 comma 4. 2 comma 4 is 12. 0 plus 12. 1 comma 2 is 10. 1 comma 2 is 2 plus 3 comma 4 is 3. 3. 1 comma 3 is 10 plus 4 comma 4 is 0. So which one of this is minimum? This is minimum. So this is 5 plus 11 is 16. So cost of this one is 16. Right? So answer is 16. And who gave this? Which was the root here? Here the root was 2 and here the root was 3. This was the root. So 3 is a root again. Now next, j minus I equal to 4, then I should consider 4 keys. So for this possibility is 0, 4 minus 0, that is 0 comma 4. So finally I have to find out this value, last value. So for that, all possible binary search trees, from that I have to pick up the best one. That's going to give me a optimal cost. Now I will directly use the formula and solve that one. So cost of 0 to 4. So ignore 0. I have to take key 1, 2, 3, 4, that are 10, 20, 30 and 40, and their frequencies are 4, 2, 6, 3. Then the weight of 0 to 4 will be how much? Add all these. So this is 15. And the cost of 0, 4 will be minimum of, if I consider first key as a root, then this is 0, 0 plus C of 1, 4. Then if I consider this second as a root, then this is C of 0, 1 plus C of second as a root, so 2 to 4. Then third one as a root, so C of 0, 2 plus C of 3, 4. Then last one is C of 0, 3 plus C of 4, 4. And in all these I should add this weight, that is 15. Right? So I will write down their values here. So this is 0 plus 1, 4 is how much? 1, 4 is 16. Plus 0, 1 is 4. Plus 2, 4. 2, 4 is 12. 4 plus 12. This is 0, 2, that is 8. And 8 plus 3, 4 is 3. 3. 0, 3. 0, 3 is 20. Plus 4, 4 is 0 only. So out of this, which is giving minimum result? This is 16 and this is also 16 and this is 11 and this is 20. So minimum answer is 11 plus 15. And who is a root here? 3 is a root here. So answer is cost is 26 and 3 is a root. So this is 26 and 3 is a root. So the cost of optimal binary search tree is 26 and root is 3. Now I have to generate a tree. Let us generate a tree from this data. This is 0, 4 and the root is 3. So for root of 0, 4 is 3. So if I take third key as a root, this is a key number, not a key, that is 30 is a key, this is a key number. Then on this side what we will get? Root of 0 to 2 and this is root of 3 to 4. Now 0 to 2, 0 to 2 is this one. So who is the root here? 1. So for this, root is 1. Then on this side what I get? Root of, when 1 is the root, 0 to 0. And on this side, root of 1 to 2. Then who is root of 1 to 2? 1 to 2 is this one, 2. This is the second key, right? This is the second key. First key and the second key. So that is second key is the root. So here is the second key is the root. Then on this side what it will be? Root of 1 to 1 and this side root of 2 to 2. So for this answers are 0 only. Now 3 to 4. So what is 3 to 4? 3 to 4 is this one. This is fourth key. So this is fourth key. And on this side root of 3 to 3 and root of 4 to 4. So for this all the values are 0 only. So this is a tree. So who should be a root? 30 should be a root. And the left hand side should be 10. Right side of this one should be 20. And the right side of this is 40. That's it. This is the optimal binary search tree. For this, the cost of searching will be minimum based on their frequency of search. Now finally, I will write on the formula that I was using. Cost of I comma j is equals to minimum of cost of I comma k minus 1 plus cost of k to j plus weight of I comma j, where k takes the values greater than I less than equal to j. So the root was not starting from I afterwards. So if this is 0 comma 4, so we'll start from 1 onwards, ignore 0. That is the meaning. So this is the formula for optimal binary search tree, and the same formula I was using it for filling the table. So that's all about optimal binary search tree problem.